The fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
Cool. So hello, everyone. My name's Ben, and today I'm going to be talking about PGAS and how it is a useful abstraction for building distributed data structures in C++. So first, a little bit about me. I am a PhD candidate over in Berkeley, where I'm advised by Kathy Yellick and Aiden Bullich. We work on a lot of large-scale parallel systems. Both Kathy and Aiden are also jointly appointed over at Lawrence Berkeley National Lab. So we do a lot of work on LBL and ORNL supercomputers. So a lot of this work is targeted kind of at the scientific simulation and HPC communities. So first, I'll start out with a little bit of background. So first of all, what is a supercomputer? How would we write a program that would run on one? Then we'll talk about the actual PGAS model and what it means. A hardware technology called RDMA that really enables PGAS to be performant and is becoming more and more ubiquitous. We'll talk about building remote pointer types, which is really the core abstraction enabled by PGAS that you can use to then build data structures. We'll talk about how you build maybe one or two of those data structures. And then finally, we'll round out with some points about how this model works when extending it to work on GPUs. Okay, also what this talk is not is, here is my distributed implementation of the STL and everything is conformant and all that. I will present some STL-like data structures, but I'm not trying to claim that they're perfectly conformant or anything. But this is just taking PGAS basically to its conclusion when it comes to building useful data structures. And then second, I'm not trying to claim here that we've established that PGAS is better than any other parallel programming model. This is simply an exploration. Okay, so first some background. What is a supercomputer and how would we write a program that runs on one? So a supercomputer or a cluster is a collection of some nodes that are connected by a network. So here in the center, we have a bunch of computers, nice old-timey ones. They're all connected by some kind of a network, and they can send and receive messages over this network. And they're going to work together to solve some problem. Up in the upper right, we've got what an actual supercomputer, in this case Summit, which is in Oak Ridge, looks like. And these are very useful for scientific simulations, large-scale graph calculations, all kinds of stuff. Now, when it comes to actually programming them, there are two main programming models that are in use today. There are more than this, but these are kind of the most basic ones that are enabled by hardware. The first of which is message passing. So here we have two nodes, node 0 and node 1. And node 0 wants to send a message over to node 1. So node 0 will say, please send a message to node 1. And then node 1 will say, somewhere in its code as well, please receive a message from from node number 0. Now the thing that's important here is that somewhere in the code on these two nodes, in their separate programs, there has to be a send and a receive. So not only does process 0 need to know that he's going to send this message, right, when he calls this MPI send command, process 1 needs to know around the same time that he's receiving it. Right, so we've produced some data over on process 0. We're sending it, and then at the same time, process 0 is preparing a buffer where he's going to receive that data. He's calling the receive command to receive it, and then process 1 now has this data. And the key here is that process 0 and process 1 both have to participate. An alternative to this is RDMA-based communication or one-sided based communication. So here, there is a portion of memory, which is located on node number 0, that has been opened up so that other processes or nodes can access it over the network. So here, node 0 happens to have some reference that he can use, some window into the memory of node number 1, and he's saying, hey, I want to write to this memory location within node 1's shared segment that's been opened up to me. And And the key here is that this is a one-sided operation, right? So this is only happening in the code on process number 0, right? Process 0 prepares his data, he gets from some algorithm, and then he can use some kind of a fancy mem copy with this remote reference, this remote pointer that he has into the memory on node number 0 to do a write into that node. So process number 1 never needs to be aware that this mem copy is happening. It's entirely a one-sided operation. So this process 1 does not participate in the write. Now the PGAS model is a specific parallel computing model where you assume that each process is going to have its own shared segment that is opened up. So here we can assume we have a program that's running with 4 processes, process number 0, 1, 2, and 3. And each of them have their own shared segment, which is shown here with the box. So this is a globally addressable space of memory, right? Anywhere within these shared segments, we can get a pointer, and we can dereference that pointer and write into these memories. But it's also partitioned, right? So process 0's shared segment is distinct from process 1's shared segment, and so forth. So that's where we get partitioned global address space is a name for PGAS. So this is simply RDMA communication, where we assume that everyone has a shared segment, and that's how we're going to do our communication. So here we've got process 1 and process 0 have some pointers into somewhere in the memory on process 2. Similarly, process 1 could have some pointers into the memory on process 0 and process 1, and then could go and write to those pointers to do communication. Now, why would you want to use this model? So modern supercomputers have had, indeed for some time, past decade, hardware capabilities that make this kind of memory access very, very efficient, called RDMA, or remote direct memory access. So essentially what happens is when we have this node here, over on the right, the big node, and he wants to write somewhere into the memory on this other node, the small node, the CPU will communicate with the network interface card, which has basically a DMA engine inside of it. And then the NIC will go to the DRAM, and it will copy the data over into the DRAM on the remote side using the NIC. So the network interface card on both sides can directly access the memory, and the CPU doesn't need to be involved with this. So this can lead to very, very fast, like microsecond accesses. And also, there's an advantage that you don't have to worry about attentiveness, right? So you don't have to worry about whether the CPU is going to enter some kind of a progress loop or whether the program is aware that it's supposed to be receiving a message. And this is very useful because it allows for irregular one-sided accesses that are very fine-grained and very low latency. And it's also useful because this kind of access maps well onto data structure operations. The kind of data structure operations we're accustomed to, like inserting into a map, writing to a vector, reading from a data structure. These are all one-sided operations, and so if we're trying to implement them, it's useful if we have a one-sided protocol with which to do so. Okay, so before we get into looking at actual code, I want to cover one quick quirk of writing programs that run on parallel computers, just because people may not be familiar with it. So when we write code that runs on a computer, typically we have multiple processes, which may be living on other nodes within this cluster system. Each process has got its own memory space, and there are basically 2 methods of communication, shared memory and message passing. So when we implement a program, we typically do it in what's called the SPIMD style. So what this means is we have a single program that is going to be run on a bunch of different processes. So here we've got a program. It has an init statement, which kind of initializes this distributed runtime. And then we have a single statement, right, which would print out a line of code. Now, when we actually go and run this code on a cluster, right, I want to point out that this code is going to run 4 times because there's a copy of this program running on 4 different processes. And this is configurable at runtime. So each process is running the same program. And we can have this particular process take a particular path by using if statements. So you can say if your rank is rank number 2, then run this statement of code, and we can see it only prints out once, right? Because only one process is running it. This is important because if you use kind of a fork and join model in a distributed setting, it can lead to scalability issues. Like if you're running your program on 1,000 different nodes, you don't want to be spawning these remote processes all across your cluster because that presents a huge bottleneck. Okay. All right, so let's talk first about the remote pointer abstraction that allows us to reference memory on other nodes and how we can implement that in C++. So remote pointers are a type of smart pointer that can reference memory that lives on another node, that can reference remote memory. And we can use a remote pointer to perform a get and a put operation on the remote node. And we've already kind of seen how you can do that a little bit with a memcopy operation. So you can implement methods that take in the smart pointers and then will perform regular gets and puts. You can also implement methods that will perform atomic operations. And if you have a local pointer or a global pointer, excuse me, a remote pointer that happens to be on the current process, you can convert it into a local pointer. So then you could do local memory operations. So let's take a look at what this could look like if we implement it. So here we have a struct, right? And it has a template type T. So it's going to be a pointer that's pointing at some elements of some type. And it has two things associated with it. First is a rank, which is a process ID within all the processes in your program. And the second is an offset, which is the offset within that process's shared memory segment that we're actually referencing. So we can then we can implement methods which will perform remote communication using these pointers. So we can implement a memcopy function. Here we have a remote pointer, and we want to read data from that pointer. So we're copying from source, which is a remote location, to dest, which is a local location. So we're going to, in our actual implementation, end up calling a remote get function. This is going to be executed in RDMA, and then we can get the data. And you can imagine how we might, flop the types of the dest and the source, and then we're doing a write, a remote put, instead of a source. And you can also implement, like fetch and add and other operations using your remote pointer type. Another thing you can do, in addition to all these, is dereferencing your remote pointer. However, now when you dereference a remote pointer, you don't get a raw C++ reference. And that's because it's not possible to get a raw C++ reference to memory that lives in the address space of another process, assuming it's on another node, right? You can have multi-process memory within one node, but if you're moving across nodes, you can only do it using these RDMA-based libraries. So the thing that you get back is a custom reference type, which we call a global reference. And then we're going to be we can implement a global reference, which does the things that we would expect from a C++ reference type. So we can say, I would like to assign to this reference, meaning I would like to assign a value to this memory location. That's going to result in something like a memcopy, assuming that we have trivially copyable types, of course. And we can perform an implicit conversion, right, to read from the value. Okay, so now we have these remote pointers. They allow referencing memory that lives on another process, and they can support all kinds of nice memory operations, including dereferencing, with the limitation that we have to have a custom reference type. But they're limited to trivially copyable types. Now, when it comes to data structures, we can move beyond this and store non-trivially copyable types as well. But we'll discuss that later. So let's quickly look at what using one of these pointers looks like inside a program. So here we have a global pointer that we're declaring. And remember, since we're writing a SPMD program that is run on a number of different processes, there are actually going to be 4 different copies of this pointer, all living on different processes or different ranks. So we have rank 0, 1, 2, 3. So when it starts out, they're all null. And then on a particular process, we can allocate some memory, which is what we're doing on process here. And so now the pointer has a value. We can then perform a broadcast operation, which is a collective operation that sets the value of pointer, basically broadcast the value from process number 0 to all the other processors, so now they all have the pointer. And then they can all perform their writes. Okay, so hopefully you have a little bit of an idea of how remote pointers can work. So let's talk about how you build a data structure on top of this. So data structures are split into two types when it comes to just like memory or data structures that are accessible in a distributed way. So the first is remote data structures. These are not actually distributed. They live on a single process, but they are globally accessible. And a good example of this would be something like a queue. So we have a queue data structure that lives on rank number 2 here. However, it's accessible by all the other processes. So we can see in the animation, we have rank number 0 inserting into this queue. And this is useful for shipping data around in an asynchronous way and so forth. So you can see all the other ranks are able to insert into this queue. Another type of data structure is distributed. So here, not only do we have global access, but also the data will be automatically distributed among many processes, or either all the processes or some subset of the processes which we pick. So here we can see we have a distributed hash table, which is split among a bunch of processes, and then we have people inserting into the hash table. So when it comes to actually using one of these data structures, the constructors and the destructors are called collectively. So here, and what that means is just that they all call the constructor and the destructor at the same time. So here we have one of these SPMD programs that we've written. So we have a BCL hash map data structure, which is kind of an unordered map like data structure that we've created. And then it's going to be distributed among all of the different processes, and then we can, for example, have rank number 0 insert a bunch of values into this hash table. So each process invokes the constructor collectively, and then each process is going to have a global view of the data structure, and we have rank 0 inserting into the data structure. When it comes to iteration, we have two different concepts. One of them is global iteration, which is analogous to iteration over a normal C++ container. So we have a begin and an end, and then we can iterate over all of the things that are stored in this hash map in a distributed fashion. This will perform all the RDMA operations you need to retrieve the data under the hood. And we're using a little bit of destructuring here to get the key and the value, and then we can have them all be printed out by rank number 0. The second concept is local iteration. So here we have a local begin and a local end, which reference only the portion of data which is present locally on the process that is calling local begin and local end. And so here we have rank number 0 just printing out its portion of the hash table that it owns. Okay, so let's take a look at how one of these data structures would be implemented. Specifically looking at a distributed hash table. So we have a distributed array, which is split up among a bunch of processors. So here we have process 0 owning the first block, process 1 owning the second block, and so on. Each process has a local copy of pointers to each of these data structures, or each of these portions of the array. So each process can manipulate all parts of this distributed array collectively. Okay, so let's talk about how you would insert into a distributed hash table in this case. So here let's suppose that we've called insert. So we want to insert a key and a value into this distributed hash table. The first thing that we have to do is calculate the location that we want to insert this into the hash table. Or at least the first location we want to try. This is probably pretty familiar to you guys. The first thing you do is you basically use an atomic operation to request to write a value into that bucket. That's one RDMA atomic operation that you've done, fetch an op. Then, assuming it's successful, you insert an item. That's one RDMA write. And then you have a final, after that write is complete, you have a final write to signal that that bucket is ready to be read. When that comes out to the best case cost, we have two atomic operations and a write. In some cases, I won't get into this in this talk, but in some cases you can elide that final atomic. But even if you elide that final atomic, this is still a latency-bound operation, right? So it is taking advantage of basically the fastest you can do this fine-grained operation over the network, right? The atomic up will cost around 2 microseconds. The write will cost around 2 microseconds, assuming it's latency-bound. The final atomic up will cost around 2 microseconds. That's pretty fast, but still, if we want to insert a bunch of items into this hash table, we would like to turn it into a bandwidth-bound operation. So how could we do that? So we introduced this concept, which we call buffers. So here we have a hash map buffer. And a hash map buffer is a little bit like a range adapter in that you give it a distributed data structure, and then you can perform operations on that buffer like you would on the original data structure. However, what it does is it relaxes the guarantees about when the operations that you've issued will take place. So here we can create a hash table, and then we can create a hash map buffer on top of that, and then insert into the hash map buffer. However, these inserts will be relaxed so that they only occur. Oh yeah, I've got some highlighting. So first we create this hash map buffer, and then we perform a bunch of inserts. However, these inserts will be delayed or will be relaxed, not guaranteed to complete until we call this final buff.flush. So this is basically an adapter on top of our container that will relax the guarantees about when things complete. How does this work under the hood? I'll give you a very brief overview, but basically what it does is the buffer has some data associated with it, this kind of queue messaging structure. So we use the queues that we talked about earlier, put one on each process, and then we can insert data into these queues, and then the queue basically being on the node where we want to perform the insert. At some point, the node that is receiving the message will pull it off the queue and then do a local insert, which is much faster than doing a remote insert. And this actually leads to a significant performance boost, as you might expect. So there's about a 3.7% improvement in this particular benchmark, which does have a bulk insertion phase, but also has some fine-grained iteration as well over the data structure. We're also able to match kind of using these programs that are written using these high-level data structures, match the performance that you get with expert-tuned implementations, assuming we have the correct data structure. If you look at the number of lines of code, obviously we've taken something that is very low level, essentially includes a custom implementation of a hash table over here on the right, and then we've replaced it with something that is using high-level C++ data structures, so it's much more concise. So we've implemented a whole bunch of different data structures using this model, ranging from Bloom filters to queues, suffix arrays, and hash tables. And so this is generally how we've created data structures on CPUs. So I'll stop here. I'm about to move over to GPUs, but first ask if there are any questions before I go on. Yeah. So yeah, so the question was, is BCL available? Is it open source? So yeah, BSD is available. It's BCL is available. It's like BSD licensed or whatever. So yeah, it's available to use, and you're welcome to contribute to it also if you like. I will say that it is research code, right? I'm an academic, and so I try to build usable and reliable APIs, but depending on what particular data structure you're looking at, I'm not going to claim that it matches the semantics of the C++ standard template library exactly. But. Okay, yeah.
So a few times you said do an operation collectively, which sounded like there's a synchronization that has to happen. Is that what's going on, or what does that mean?
Yes, yeah, so that was a great question. So a couple of times I mentioned doing an operation collectively. So what does that mean? Is that expensive? Does it require a synchronization? What's going on there? So what a collective operation means is that all of the processes are going to do something together. So at the very least, it's going to be the equivalent of a barrier, right? Meaning no process can leave the barrier until at least all the other processes have entered the barrier. But it may be something more than that, right? So it could involve communication. In my case, so it does enforce synchronization when you do a collective operation, but we're only really using the collective operations for like bookkeeping. Things like passing these remote pointers around, and then all of the main data structure operations that we're performing, we do using the remote pointer abstraction that's executed over RDMA. And that is asynchronous. It doesn't require collectives. Yeah?
For your remote pointer operation, when you returned it, I believe you casted your T to a pointer and then you referenced that. So like, why not just return the T directly for your pointer, global pointer route?
Okay, yeah. So the question was, when we had the global pointer and we dereferenced it, we didn't just return a type T, we returned a global reference type, and then we went and dereferenced that. Right? Is that the question? Oh, let me go back. One second.
Yeah, right there. Like operator T, right? Why did you just return the value? Why that last? You static cast.
Oh, why do we have this static cast? Oh, yes, okay. Yeah, so this is not actually the code that I wrote. I wrote this to be short and on the slide. So yes, you're absolutely correct. So normally I would avoid using actually T. I would use a buffer that is going to be not default constructed, that is of size T. That way you avoid like default constructing T if that's something that you were going to do. Yeah, that's the only reason for the static cast. That's an artifact of my copying it to the slide. Yeah. Yeah, you were first. Go ahead.
How do you maintain shared metadata? Let's say in HashMap, you at least need to maintain number of buckets and size of queue. In case you do resize, you need to update the shared metadata. And given you have every machine have its own memory, how do you keep it synchronous? How to maintain this metadata?
Right. So the question was about metadata. If we resize the hash table, how do we make sure that everyone knows what the new sizes are and stuff like that? So one of the limitations of this hash table design that I've presented is that it is not dynamically resizable. So if you want to resize the hash table to contain more elements, then you need to actually go and have a collective resizing operation. For the HPC applications we're used to looking at, a dynamically sized hash table is actually not super necessary. We have looked at dynamically sized hash tables and implemented some. It comes at the cost of basically two additional memory operations. And you can do this in terms of the metadata, basically by having a globally stored pointer instead of a locally stored pointer that can be updated atomically. Yeah, so hopefully that answers your question. All right, well, yeah, one more question, and then I'm going to get on GPUs.
It's kind of an extension of that question as well. HashMap buffer is relaxing the guarantee of the, I guess, the timing of the write. How do you deal with conflicts or like concurrent writes in that scenario?
That's a great question. So HashMap buffer is relaxing the guarantees in terms of when the writes happen. So how do we deal with conflicts? So our semantics are that basically you've done two writes that happened at the same time. Assuming that you started a HashMap buffer, you did a bunch of inserts, some of them conflicted, and then you did a flush operation. There's no ordering between those two operations. So basically, it's undefined which of those values it's going to be in the hash table, but it will be one of those values.
And that's even across two different servers, not just two writes on the same node. Because two writes on the same node would default to having the last.
That's even across as well. Yeah. Okay. All right. So let's go ahead and move on to GPUs. So GPUs are more and more ubiquitous, and particularly for us in the supercomputing world, more and more of the big supercomputers are deriving a lot of their power from GPUs. And GPUs come with a lot of challenges, right? They generally have something on the order of 10 times more compute and more memory bandwidth than traditional CPUs would. just in case anyone's unfamiliar with what a GPU is, right? For our purposes, it is something, we have our CPU here, which is on a node, and then we have a PCI bus or some other fast fabric which connects this GPU that's sitting off to the side, so they can perform some computation together. There's actually a third entity in this mix, which is the NIC, or the network interface card. So historically, when you wanted to do communication, and you had some data on a GPU, you wanted to write it to another GPU, then you would have to do a little bit of orchestration. So first, you would take the data that was living on the GPU, you would copy it over this slow PCI bus, it would find its way to the CPU, and then you would copy that data over the network. And it would go to some node, and then you would have to do this orchestration on the other side as well. But however, recent network technologies such as NVIDIA's GPU Direct RDMA, AMD has similar stuff they're working on, although I don't remember what their branding is. But new technologies allow for direct GPU access over InfiniBand. So we can submit an InfiniBand request to the NIC and say, hey, I have this data on a GPU. I want to copy it directly over the network from this GPU to a GPU living on another node. So instead of having the data go through the CPU, the data first goes to the network interface card, goes to the other node, and then is deposited on the remote GPU. This can actually today be initiated both by the CPU and by the GPU. So all of the major GPU vendors are working on libraries to allow the GPU to talk directly to the NIC. On the other hand, we also have more and more fast in-node fabrics. NVLink is one example from NVIDIA. AMD also has Infinity Fabric, and I'm sure Intel is coming up with something similar that allow for fast intranode transfers. So typically we don't just have one GPU on a node, but we have a whole bunch. Could be as high as 16, or there are some special systems that have like way more, but generally on one of our systems, the max is like 8 or 16. And basically what you do is you replace this slow PCI fabric with a fast intranode fabric, and then all of the GPUs can talk to each other over this network. There are a bunch of different communication libraries that enable GPU to GPU communication, from CUDA-aware MPI, which is probably the most ubiquitous, to things like GASNet. In this talk, I'm going to focus more on the libraries that are more PGAS oriented. And specifically what we looked into is using NVSHMEM to build remote pointers that work on GPUs. AMD also has a similar offering. But the MPI and the GASNet implementations are currently limited to CPU-initiated communication right now. Okay, so to remind everyone, when we had a pointer to remote memory which was living on the CPU, we had this pointer, and then we could allocate some memory on a particular node, broadcast that pointer so that all of the nodes have the ability to access it, and then we could go and write into that pointer. Now, what we do is we extend this to work on the GPU. So now instead of just having a normal alloc, we have a CUDA alloc, which is going to allocate memory that lives on the GPU. Now we have this special CUDA pointer, which is referencing memory that lives on the GPU. And we can access this memory. Here we're accessing the memory on the CPU. So we have the CPU, which is dereferencing a memory location, which potentially lives on a different GPU, and then writing to it. You can actually also send these pointers into a CUDA kernel. If you're not familiar, a kernel is where you write the code that actually runs on the GPU. So here we're passing this pointer in as a parameter, and then writing to that pointer using the GPU. So as you might recall, we had this global pointer type that had a rank and an offset, and then that allowed us to implement a memcopy implementation. Now we have a GPU remote pointer, and it also has associated with it a rank and an offset. Currently, this is all that's necessary because all of the libraries that I told you about only allow you in your distributed programs to associate one process per GPU. You can't have more than one GPU per process. If we did, we would probably need more here to indicate not only what process you're on, but also what GPU within that process. But for now, this is all that's required. And then we can go and implement our memcopy function. Now, the memcopy function requires some if-defs, and that's because we need to create versions of this function which will work both on the CPU and on the GPU. So if you're unfamiliar with GPU code, at the top we have a host device that says that this is a method that can run either on the host, the CPU, or the device, that's the GPU. And then we can use this if-def basically like an if-const expr to say, if we're running on the GPU, then I want to call this particular method. Otherwise, I want to handle the logic for the CPU. I won't show the actual code here because it's slightly messy, but currently, if you're on the CPU accessing memory, in PGAS, you need to have GPU memory that you're using to write to the remote GPU. So there may be there's a little bit of orchestration necessary there on the CPU side, but that's accessing the pointers on the CPU side is mostly a convenience thing from the standpoint, if you're doing individual element access. Okay, so when it comes to implementing one of these data structures, recall that each process has this table of pointers that it uses to access the data. These remote pointers into data that lives on different nodes. So now this is going to become, instead of this RDMA accessible memory that lives on the host, RDMA accessible memory that lives on the GPU. So instead of being associated just with process 0's CPU, now it's associated with process 0's GPU. Also, if we want to implement GPU side methods, we're also going to need a copy of this GPU side remote, of this pointer table that lives on the GPU side, so that when we're inside a CUDA kernel and we're calling a method, we know what these pointers are. So okay, then you come to a question, which is having this enough to implement GPU side data structure methods? Can we just go ahead and copy this data structure to the GPU, inside a GPU kernel, and run it? So it turns out the answer is no. And this is actually because of the semantics of what happens when you pass an object into a CUDA kernel. So okay, here we have this CUDA hash map object, right, which is this distributed data structure which lives on the GPUs, or its data lives on the GPUs, but it's just a local object on each process, and we're handing it in as an argument into this kernel, right? So this kernel is going to be called, and it's going to receive this object. So the order of things that happens when this object is passed into the hash map is first the copy constructor is invoked on the host. This new object is going to be trivially copied to the GPU, or mem copied to the GPU. Then the GPU kernel is going to be executed asynchronously, so it may complete at some point in the future. And then finally, this destructor is going to be called. But the destructor could be called actually before the GPU kernel is executed. And the destructor is called on the CPU. These are not really the semantics we want, right? When we pass a data structure into a CUDA kernel, what we want to do is we actually want to have access to the data structure, not a copy of the data structure. We can pass in, I will say, a reference to this data structure using CUDA malloc managed memory. However, that comes with a little bit of a performance cost, but more than that, it's a little bit inelegant when it comes to how you have to create the data structure. Because you have to create it using this special CUDA malloc managed function, and then you have to placement new inside this data structure. However, so what we want to do is we want to have this copy constructible placeholder object that we can just copy into a CUDA kernel and then call methods on it to perform manipulations on the data structure. And so what we can do to use this is actually a view. Because a view is exactly that. It is a non-owning entity that has a reference to this data structure. It has an O of 1 copy constructor. So it's not going to create a copy of the data. It will just reference the original data. And we can send this into a CUDA kernel, and everything will be nice. So here what we do, we have a data structure that we've allocated on the CPU side. We created a view, which we then passed into this CUDA kernel, which will be sent to the GPU. and we can call methods on it, and they will manipulate the original data. All right. Are there any? Okay, I'll just wrap up really quickly, and then we can take any questions. Remote pointer types, hopefully we've learned, are a useful abstraction for implementing distributed data structures. We can implement a variety of different data structures. They are extendable to multi-GPU data structures. And we're able to get good performance by having the correct, highly tuned distributed data structures to unlock performance that is competitive with highly tuned implementations. I'll just show up some quick pointers quickly before I take questions. So I've got a link here to our code if you're interested in it, and also a pointer to my website where there are links to the BCL repo and also a bunch of our papers if you're interested in the more academic side of things. The QR code is also to my website. I also want to say another thing you can do if you're interested in this kind of irregular data structure, or this kind of thing. I would recommend that you check out another talk that Scott and I gave at CppCon yesterday, which is on GraphBLAS, which is a linear algebra library for implementing graph algorithms. And also, yeah, you can hire me because I'm graduating soon. So, okay, yeah, with that, I'll take questions.
So
yeah, go ahead.
If you don't have fancy NIC cards to distribute the memory around, does this still work, or is it just slower, or is the dramatic performance drop?
That is an excellent question. Okay, so the question was, if you're not running on a supercomputer, you don't have these fancy NICs, what happens? Is this just become terribly slow? So the first thing I would point out is that RDMA is becoming more and more ubiquitous. So I think the chances that you actually do have it are becoming higher and higher. If you're using something like AWS, the NICs that they actually use support RDMA. And I don't know the specific details on which vendor does and does not give you support for RDMA, but they're working to expose that capability through their virtual network interface drivers. Back when I did a bunch of experimentation back in 2018, that was not the case. So I actually got to see what happens when you don't have what happens when you don't have RDMA. And the answer is your performance suffers, right? And the latencies go from something like 2 microseconds for an RDMA read operation, or basically a read or write in atomic, it's all pretty similar, to something like 6 to 8 seconds, depending on a number of things. So the first thing to note is that when you're using an RDMA primitive and you don't have RDMA, it's basically emulated using progress. So you have some kind of a communication runtime. When you send an RDMA request basically to the remote node, it's not being handled automatically by the NIC. It's going into some kind of a queue. And only when that remote process dequeues from that and handles it, are you going to get your operation to finish. So it can actually vary depending on the application. We actually have a paper that looks a little bit into this. It's called RDMA versus RPC for distributed data structures. In one of our papers, we have actually the numbers that I got back in 2018 on AWS. And the answer was it's still pretty comparable to what you get if you implement it using MPI. In terms of the overall performance, even for relatively fine-grained applications. But I will say that the things like the hash map buffer become even more important, right? Because the latency associated with the fine-grained access becomes even more onerous. Yeah. Okay. Next question. Yeah.
Your comparison with Chattel was interesting, and I was wondering whether today with postmodern C++, we can actually hit all these PGAS languages.
So that's a great question, yeah. So the question was essentially, we did a comparison with Chapel, which was interesting. Does that mean that today we can beat all of these PGAS programming languages with modern C++? So I will say we can do a great deal. So my advisor is actually most known for working on UPC, which is one of the big parallel programming, at least historically, one of the big parallel programming languages for PGAS languages. And you can definitely do compiler optimizations inside a PGAS programming language that knows the semantics of the memory model, like knows what the remote memory is, that you can't do with C++. Right? Like in Chapel, you could do a transformation, and in fact, they do some of these transformations where you identify that you're doing a loop, and then you're able to batch these memory accesses, kind of like we do. Again, they are kind of relaxing their consistency model when they do that. But yeah, I think there's a great deal that we can do, and I think with more of the C++ features that are coming out, there'll be even more. But yeah, it's a great question. Okay.
I'm assuming the BCL non-copy implemented was blocking, correct? Or is there like a buffer non-copy that's similar to the HashMap buffer? The way you can make a memory operation asynchronous. What I'm thinking of is like a fire or hit message that you have to keep that memory valid for that mem copy before it finishes. But then as soon as it finishes, maybe you just have to clean up code that
So that was an excellent question, which was about BCL memcopy. So in the memcopy, is that a blocking memcopy? Is there a way to do asynchronous copying in BCL? What is the memory model? What are the guarantees about when your writes and your reads complete? So in this talk, there's a whole, or in this work, there's a whole like memory model that I didn't even talk about, right? So the BCL memcopy follows the OpenSHMEM model for blocking, what they call blocking puts and gets. Essentially what that means is that your get is going to be visible to you. So if you do a mem copy into your local memory, it's going to be visible to you as soon as it completes. So that's completely blocking. If you do a put, that will appear visible to you as soon as the put completes. So if you're doing a mem copy into a remote memory region, but it may not be visible to other people until you issue a flush operation, or there's a barrier, which is equivalent to a flush. We also have support for asynchronous memory operations, both on the CPU and the GPU. There's a whole asynchronous bit with requests, which are basically handles that you can call basically wait on in order to ensure that a operation has completed, and with futures. So for example, on many of the data structures, there are asynchronous versions of the methods. For example, with a matrix data structure, you can say, please give me a certain tile of this matrix, and that'll be blocking, but you can say async get tile, and that will be non-blocking. It will return to you a future object, and then when you call get on that future object, you can retrieve it. They're not standard futures, but they are standard future compliant. Yeah.
Because I know there's all kinds of like issues with standard features that defines, invoke Sean parents and tell us a whole lot, but yeah.
Yeah. Okay. Oh, yeah.
Yeah, it's a typical use case for the future smart reference we need in C++. Because then you could replace a lot of pointers.
Yeah.
It would be that efficient, probably, but change a little bit the user experience.
Yeah, that's a good point. Yeah.
So for thread safety, I'm guessing you need a whole other distributed log.
Yes. So, okay, is your question about thread safety? Right. So the threads within one process, yes. Or, okay, yeah.
So the process is running on all four. Let's say it's a multi-thread.
Yeah. So the question was about, we talked about having multiple processes that are all accessing the data structure. What about multi-threading? So It depends. So some of the data structures, if you use them with multiple threads and you basically compile with a backend that in a way that is thread safe. So for example, you're using MPI, the MPI backend, and you started with MPI thread multiple, which is saying basically I want to enable multiple threads to call MPI functions at the same time, then many of the data structure operations will work. I'm mostly not really targeting a multi-threaded environment where all the threads are calling the data structure methods. But yeah, they'll all obviously work if you have a multi-threaded environment and then you funnel your data structure operations through a single thread that calls the operations, because then it's essentially the same as the process-based. Just your process happens to do some stuff with threads sometimes. Yeah. Okay. All right. Well, thanks so much, everyone.